So the next ones we're going to look at then are the ray diagrams for curved mirrors. Now there'll be a lot of similarities between the mirrors and the lenses, however, also a few key differences. So first of all, we still have those terms, the concave and the convex. They have a similar sort of meaning. So a concave means that you have that inward curvature to this one overall, and then the convex, you have this outward curvature. Now here, there's only going to be just really one side to that because it's a mirror. That's one of the main things, or main differences between the mirrors and the lenses. On the lenses, you're looking through the lens, and so your eye and the object are on opposite sides. With the mirror surfaces, we're dealing with a reflection, not a refraction, and so your eye and the image are going to be on the same side. And so if you put your eye over here, and it will have this mirrored surface on the inside, basically your eye and the image, the thing that you're looking at, are all going to be on the same side of the mirror. For on this one over here, our eye is looking in this direction, and then we're looking at this mirrored surface over here. Now because there's only one side, we do very often just kind of put dashes on the non-mirrored side, just to keep the two sides of the mirror straight. Now the other really big difference is basically that concave convex and how it relates to converging and diverging. And so your concave mirror is the converging mirror. Now you'll note that that's opposite then for lenses. So for lenses, the convex lens is the converging lens. For mirrors, it's the concave mirror, then that's the converging one. And if you remember just what converging means, it just means if I have parallel rays coming in, they're all going to converge to some point. Now that's going to be on that focal point always, but if I draw parallel rays, and I can draw them in on several points there, all parallel rays are going to get reflected, in this case, back through that focal point. And that's going to be the concave mirror then. And again, just watch for that difference there. For the convex mirror then is going to be the diverging mirror. Of course, is again just opposite from the lenses there. And these ones are going to spread apart. And so if I have a parallel ray coming in here, it's going to be reflected such that it heads off in some direction like that. Now that is going to be such that it appears to come from this focal point. But again, the light never does actually go there. The light, remember, always stays on the reflected side of the mirror here. But if we extend the reflected rays back, they will appear at least to come through this focal point. Now this one's referred to then as a real focal point because the light rays do actually go through there. That's with the converging. With the convex, the diverging mirrors, the light rays never actually get to this focal point. Again, remember, they stay on this side of the mirror because they're just being reflected off of the surface. And so it is a virtual one because the light doesn't go there, it just appears to go through there. And so it is a bit of an optical illusion, but we can use that point then still to come up with the image position. So a number of terms that are going to be similar between the lenses and mirrors. We still have our principal axis here. And your principal axis, remember, is just that line. It's going to be always drawn perpendicular to the mirror surface, and it goes right through the center. Now our object and our image are always going to have their base on this line, and then we'll try to figure out where the top of that image is relative to both of those. We have our focal points, and the focal points again are a bit different. With the lens, we have two focal points, one on each side, because the light's going through the lens. With these ones here, because we have a reflection, all the light stays on one side, so there is only the one focal point then with the mirrors. Now on our lenses, we also had the second point out here, which we used for some of our image characteristics, which was the 2f, which is twice the focal point. On our mirror, that's going to be something called the center of curvature. Now it functions in the same way, and so your image characteristics are going to be the same between the lenses and mirrors relative to that center of curvature, and it's always at that point 2f. This one here, though, just does depend only on the curvature of the mirror. With the lenses, basically the focal point depended on the curvature and also the material, because that would always determine how much it refracts. With the reflections there, it doesn't really matter what you make this out of as long as it's a mirrored type of surface. It's the curvature of the mirror that depends where the focal point is. And then basically if you extend this all the way around in just one large circle, the center of that one will always be that center of curvature. And it turns out that the focal point always ends up being halfway between the center of curvature and the surface of the mirror. Now with our ray diagrams, we're going to be looking at the same kind of image properties that we were looking at with the lenses. And so as we look for the beams of light going through the mirror of the lens, we're trying to find the characteristics of the image. So first of all, you have your image size, and the images can be larger, smaller, or they can be the same size. We have that orientation, upright or inverted, and then we have that real or virtual. Again, as before, real images are always inverted, and so once you know the orientation, you should always know the type of image. If it's upright, then it has to be a virtual image. And we'll again draw 3 different rays going through there. Once again, though, you only need to draw 2 of them actually to come up with the correct image position. So the first 2 are the ones I would recommend drawing. The third one can be drawn as well, but usually these ones are going to be a bit simpler to put together. So this first one here, any incident ray that's coming parallel to the principal axis is going to reflect through that focal point. So this is the same one that we had with the lenses. Of course, with the lens, it went through it with the refraction and then went to the focal point on the other side. For here, there is only one focal point. It'll be on the same side. So we'll draw this line coming over top of the object, and it's going to go parallel to the principal axis and then reflects back through the focal point. The other one that we have then, if I have a line that's coming through that center of curvature, so that's that 2F position, and it hits that top of the object and then goes to the mirror surface, this is always going to hit perpendicular. And if you have then a reflection that's perpendicular to the surface, it's going to go back along that same path. And so this one we can just draw a line from the mirror, top of the image, to that center of curvature, and the image always has to exist somewhere along that line. And those are the 2 easiest ones usually to draw. We do still have this third one as well, though, for coming over top of the object through the focal point and then to the mirror. That one will reflect parallel to the principal axis. And really it's just the opposite of this first one that we've done here. So the first case we'll look at then is going to be the converging case. And don't forget that's going to be for the concave mirror. And if you think of it in terms of converging and diverging, then you'll find that the image characteristics are actually the same between then the different percentages or different positions for the lenses and the mirrors. And so it's generally easy to think of it in terms of converging and diverging instead of concave and convex. So for this first one, we're looking for where you're beyond the center of curvature. Now this point here, this will be your focal point, and this one out here, that one's going to be your center of curvature. And so we have our object then that's some distance outside of that center of curvature. So we have that parallel ray going over the top of the object, hitting the mirror, and then coming back through the focal point. So somewhere along this reflected ray then the image has to form. The other one we'll do then is we'll head straight through that center of curvature to the mirror surface. That one has to reflect back on the same path. And we don't need to draw the blue line here, because where this red reflected ray and this green line converge, or cross, then I'm going to get my image forming. Now the base of the image is always going to be still tied to that principal axis, so I just need to draw my arrow down to where I get the crossing of those lines. Now you could draw the blue line still in there as well, and it'll go through the same position. And what we'll see here is if you just look at this arrow, this will be a smaller arrow than the object one was, so that's going to be smaller. It's oriented in the opposite direction, so it's inverted, and inverted images are always going to be real. We also know it's real because the reflected rays are actually going through the point where that image is being formed. So if we put the object right on that center of curvature, so this will be my center of curvature here, this will be my focal point. And so we have one ray going parallel and coming back through then the focal point. And then if we go through that focal point, it'll come back parallel, and so then we get my image here. And we'll see that the image shows up basically the same distance away, and also then the same height. The only difference now is that it's going to be inverted. Now this one here can easily draw the one from the center of curvature because of course that's not going to hit the mirror surface there. So in this case we will do the red and the blue lines, and we'll leave that green one out. Now this one here, if we're between the focal point and the center of curvature, now again I've drawn the red and the blue lines, we'll talk about the green one in just a moment. Here if I have this parallel ray going through and then coming back through the focal point, what we'll see is that we're going to end up forming an image that's much larger. So I'll draw the blue line coming through the focal point, and then coming back parallel, and so we see that we get this larger image. However, it is still inverted, and so it's still then a real image as well. Now in this particular one, if we try to draw the one through the center of curvature, that is a perfectly workable line as well. If we go from the center of curvature through the top of the object and then coming straight back, that will go through this image position. One thing you will note here though, is very often when you're in this position here, when you draw that green line, so the one going through the center of curvature, it's not uncommon for this to be steep enough that this doesn't actually end up hitting the mirror, and so that can throw people off a little bit. One thing to know is it doesn't actually matter. If it, again, just always imagine, if as long as that mirror could extend out to there, whether or not it does doesn't really matter, as long as it could extend out that far, that center of curvature line through the top of the object still will go through that image position. So when you're drawing the lines, if the line you draw doesn't quite hit the mirror, just imagine that mirror just extending, and it will always match up then to the image position that you need. Now there are two cases as well then where we don't get a real image coming from the converging mirror, and this is the same for the converging lenses then as well. So the one is if you're sitting right on the focal point, and this is a case where we don't get an image forming. Now of course that blue line where you're going from the top of the object through the focal point can't be drawn here because you're sitting right on that focal point, but certainly the other two can. And so we have then the one coming parallel to that principal axis being reflected back through that focal point. And then if we draw the one from the center of curvature through the mirror surface and back again, what we'll find is just for the case where you're sitting right on the focal point, those two lines always end up being parallel to each other. And so they don't converge to a point and they don't diverge from a point. And so since they're running parallel, there's no image being formed there. And that'll be true whenever you have a converging lens or mirror and the object is sitting right on the focal point. The last case we'll get is the virtual image for these ones here. And whenever you have a converging lens or mirror and you're between the surface and the focal point, you're always going to get a virtual image. This one here, I've drawn all three lines in, and that can certainly be confusing because we're dealing with the extensions. For these virtual ones, I would highly recommend just doing two of the lines rather than all three. But they are all there just for your reference there. So the first one, this red line, is going to come through here. It's going to hit the top of that object, and it's going to reflect back through the focal point. Okay, and so those points are going to be the same. Now if we do the same thing just with this green one, we'll head through the center of curvature, it'll hit the mirror, and it'll reflect back through. Now if we just focus on those two, what we'll notice is that these two reflected rays are diverging. So because they're never going to cross on this side of the mirror, we're never going to form that real image. However then, if they're diverging rays, what I can do is I can extend those reflections backwards. And what I'm going to get then is this optical illusion here. There's no actual light going here, but your eye, basically, when it takes these diverging rays, basically projects an image back to where they've diverged from. And it creates an image there. And so what ends up happening for these ones is you get this upright image that's larger. And so for a mirrored surface, you can make things look larger by using then this converging mirror, but also then putting that object close to it so it's inside the focal point. This blue one as well, if we go up through the focal point to the object, it'll reflect parallel, and so we can extend that one back and we'll be in the same place. This one then is clearly larger, it's upright, and so it's a virtual image. Now a virtual image can also form from the diverging case, which we'll look at next, but in that case the image is always smaller. So if you have a larger virtual image, that always has to come from the converging case, and that's both for lenses and for mirrors. So the next ones we'll look at then is for the diverging case. And these ones then are going to involve virtual focal points because again, we're always dealing with the extensions from these ones here because all of our rays are going to be diverging. And so we'll always just extend the reflected rays back through then the focal point on the other side. And so these ray diagrams are a little bit different, just again, because we're dealing with a lot of the extensions to them. But the nice thing with these ones here is that the image characteristic is always the same. So these ones are always smaller, virtual, and upright. And so you don't have a lot of variation then with this side here. So there are parallels, of course, to how these ones will go with the ones we've done before. But again, we're just dealing with the extension to the reflected rays always. So if we have an incident ray that's going parallel to the principal axis, it gets reflected such that the extension of that reflected ray will go through the focal point, and it's that virtual focal point on the other side. The light never actually goes here, it just appears to come from there. But again, it's an optical illusion. This one here, the center of curvature and the focal point, they're on the opposite side of the mirror for the diverging case. So we'll draw an incident ray running straight through such that the extension would hit the center of curvature if it could actually go there, and that one just reflects back along the same line there. On the other side then, we have the one that's going through the focal point. Now this one, again, doesn't go actually through the focal point, but it's heading towards that focal point. This one I would probably draw the least just because it has two extensions, which can be confusing. But first we have the extension for the incident ray, which is coming towards that focal point. That's not where the image is lying. The image is always lying on the reflected ray. And so it's coming towards that focal point. It reflects parallel to the axis. And so if we draw then this extension to that reflected ray, the image has to form somewhere along that surface. Again, my recommendation would be using these first two for these ones, but all three will get you to the right place if you draw them correctly. So here, this would be my object, just showing up over here. This will be my image forming. So I have the red one coming parallel and then reflects so that my extension goes through that focal point. So somewhere along this dotted red line there, my image must form. Then if I draw this green line heading straight through that center of curvature, where that red and green extension lines cross, that's where my image forms. And that's enough then information then to put that one together. If we do draw this blue line in though, we will also see that this parallel extension is going through the same location. And then we get this still upright image, but it's going to be smaller always than the original object was. So that's true for all of these. It doesn't really matter where you are. You can be any distance then away from here, including the distance basically to the focal point or the center of curvature. Now you're not actually on those points because they're on the other side, but that distance, it really doesn't matter on the side. Anywhere along here, you'll always get a smaller virtual upright image.